Our next speaker is Bob Knight. He is very modest, and when I asked him how I should introduce him, he should say, "Tell them I was a star basketball player in New Jersey in the 8th grade, and I've declined since." But the truth is, Bob, in April 2017, was elected to the American Academy of Arts and Sciences. He's the founding editor of Frontiers in Human Neuroscience. He's a professor at UC Berkeley with a research program focused on human neuroscience. Welcome, Bob.
Thank you very much, Lisa. Where's Brian? Thank you, Brian, for the big ideas. It's really nice to hear. Okay, I'm going to go for a little idea instead of a big idea. I'm going to try to show you that we might be able to decode your thoughts and use it to develop a prosthetic device for people who have neurological problems. See, this is an anti-Berkeley thing. I'm positive that's what it is. What am I don't want to go here. Cancel. Thank you. Should have never put that symbol up. That's what happened. All right, so what I'm going to show you is it's basically our work, which started being funded by the NIH, and the last year we have DARPA working with us to try to develop an implantable device, not a wearable, it is wearable, permanently wearable, implantable device. So how do we get there? So we're going to go back to 1929, and Hans Berger, who discovered the EEG, was a psychiatrist. He actually discovered it because he wanted to use it to be able to divide up and segregate psychiatric disorders. And he actually showed, he actually was able to find the origin of it. Most people don't realize that. It was a technological advance. Actually recorded in surgical patients directly from the cortex. Notice this rhythmic activity. Put a needle through the cortex into the white matter and showed no electrical activity and said, hey, your EEG has got to be coming from your cerebral cortex. Kind of amazing, when you think of the time then. So fast forward, and Nathan showed you the more sophisticated signal analysis approaches that we can now use. But many of them are, traced back in large to Fourier or spectral analysis, where you take a signal, break it into its constituent subcomponents. Think of yourself in a jazz club. There's a piano, there's a bass, and there's a saxophone, and each has a different center power frequency, and you're actually extracting those frequencies. And we do that in our lab and many other labs. Now, the key thing that's happened in human neuroscience, in my perspective, in the last 10 years or so, is when I was trained, which was not 1942, but was back there a ways, people thought the highest frequency in the human brain was 50 hertz, 50 cycles per second. It's not true. If you're actually on the cortex, the most salient activity in all your brains right now, as you hear me or you look at the screen and you refocus your attention, is actually very high frequency activity in the 60 to 70 to 200 hertz range. And for the cognitive science people, more information, right? Higher frequency, more information. And this particular signal is a surrogate for underlying single cell activity in the animal or human brain. Now, how do we get at this? Well, unfortunately, 1% of people with epilepsy in this country, 1% of people in this country have epilepsy. That's about 3.5 million people. Of those, 15% are intractable, which means they don't respond to medications. But if we can find the area of the onset of the seizures, we can surgically take it out and get either control and sometimes cure of these patients. And the way you do it, to find where it is, you actually have to put electrodes directly on the brain. And they could be 1 centimeter apart, they could be 4 millimeters apart. And in many cases, probably 80% now, we actually have to insert robotically electrodes that target specific structures in the brain. Here's one going into the hippocampus. Here's one going into orbital frontal cortex. Here's one going into cingulate. You can see they're very fine wires. And I won't talk to you about this today, but at the end of these recording channels, we can actually splay out little fine wires and record actually single cells in humans, which provides a very powerful bridge between animal and human neurophysiology. So here's a patient who can't speak. He has Broca's aphasia. I'll just show you 20 seconds. He knows what he wants to say, but he can't get it out. His speech has been constrained. He has an output problem in his language, and there's hundreds of thousands of people with this. No sound, guys. Ready? Let's take the language out now. Can you tell me what happened when you had the right?
Remember, was it in the morning or the afternoon?
TV, talk about TV.
11? 11 in the morning? 11 in the morning. Okay, so he's understanding what I'm asking him, but he has non-fluent output of speech, sometimes just single utterances, but he's trying to communicate the correct content. He knows
So could we basically, that man knows what he wants to say, can I decode that signal from his brain and give him a device that would allow him to fluidly communicate with me? There's something wrong with the audio. I don't know what it is, because yeah, but I got more, we got a lot of smart people here. Can we fix it? Or because I got a lot of audio in here, it's kind of sad, but anyway. All right, so just to show you a little bit what we've done, this is the famous brain of Broca's brain from 1856. There's a lesion in the frontal lobe. This is my colleague holding the brain. We got the brain, it's been preserved, we put it in a scanner, and we actually did the MRI of the brain. And what you can see in this MRI of the brain, yes, Broca's area is gone, but there's massive underlying damage in the insula and other important connecting fibers. And this is actually 36 of our patients, like that gentleman who can't speak, and you can see the overlap of the lesion. It actually doesn't center in the cortex. It's actually subcortical. So this raises the option, the possibility that the whole idea that Broca's area is active when you speak may not be true. And if you ask 300 aphasia people, they say that can't be true. It's definitely active. Well, it turns out when you do direct brain recording and you have electrodes on the brain, you get a completely different story. So this would be an fMRI of a language task. This is a verb generation task. It's a really easy task. You give someone a noun and they have to generate an action verb, ball, kick. But it's very rich. It activates all these brain areas. The problem is you have timing problem. You've got blood flow coming on at 4 to 6 seconds, but you do the task in a second and a half. If we have electrodes directly on the brain and we do this task, you're going to see the white electrodes were where the surgical, where the tissue was taken out, so they're not included in the analysis. This is a 10-second movie, a 2-second movie expanded to 10 seconds. What you're going to see is your brain in action. Okay, you hear the stimulus, you decoded ball. You select that you're going to say kick. Look at that. You send it to your motor cortex, you resay it, and you fire auditory cortex. You've just tracked in real time your entire brain, right? You've just seen everything in action. And this technique, this direct recording, is the only technique that I'm aware of that allows you to do this with any precision. Tracking the brain in real time. Dean Flinker, who is in the lab, he's now just started as an assistant professor at NYU. He looked at this directly. What's the role of Broca's area, this critical speech output area for everybody in this room? And what he showed, he had people speaking and repeating phrases, and he gets this phenomenal high-frequency activity at 120 hertz in auditory areas when you hear ball. Broca's area comes on about 100 milliseconds after, but here's when you say kick. If you notice, Broca's area is off. It's actually shut off. So this 150-year dogma about Broca's area being active when you speak, it's just not true. So what is true? If you notice nearby, your articulators and motor cortex come on. So what's happening? If we look at the single trial level, and this is really very important for use for brain-computer interface, you can't have a technique that has to average 20 or 30 stimuli over 5 or 6 minutes or 3 minutes or 1 minute. You need something in real time. And what you see here are single trials. This is 7 subjects doing multiple trials where they hear a noun and they generate a verb. And we get reliable high-frequency activity. This is activity in the 70 to 200 range in every trial. Here's when they actually speak. And you can see beautifully, there's your superior temporal gyrus where you've decoded the meaning of ball. Here's your Broca's area, and it's pretty clear that it shuts off when you speak, and the nearby motor areas come on. So this basically led to Dean's conclusion that Broca's area is involved in articulatory planning. It's putting the things together that you're going to send to your motor system to drive your articulators, but it's not actually involved when you speak. Now, how do we use this kind of information to get at a speech prosthesis? And you've heard some very nice review of some of this by Nathan previously. You saw the aphasic patient, ALS. You pick your poison in terms of people who could benefit from a communicative device. I go back to one of my favorite first things that got me interested in this, and this is work from Jose Carmina, where he showed in monkeys, he'd record from their motor cortex. The monkeys use a joystick. They put a little ball in a big ball. They get a juice reward. They get a juice reward. Boom, right? That's well known. He's recording the motor activity. Then he trains the monkey to think about moving the little ball. There's no arm movement. It's totally being controlled by brain. And what you can see here, and this is 2003. These are old movies. It's much better now. Monkeys can, boom. Monkey's moving that little ball into the big ball simply with his thoughts. Boom, juice reward. So this was very exciting to me to see this, and we're lucky to have Jose at Berkeley now. It's extended to using EEG for driving devices. You saw some earlier. This is some stuff from Jose Del Milan's lab, wheelchair control. In a patient with quadriplegia, using brain signals alone, the patient's basically driving the wheelchair. Just by simply regulating activity in the beta range in his motor cortex. Increase beta, shut off, decrease beta, activate, left, right. It's just a 2-vector control. You can see all the gear you need, the electrodes, the amplifiers, the computer, et cetera. And I'll show you a little bit later, this is the entire system miniaturized into a 34-channel wireless dry EEG system that can do everything that this particular system can do. So this makes it much more efficacious for use in the home. It makes it cheaper and much more efficacious to get into the third world, right? Where you saw that slide where Africa has almost no neurologists, and I'll get back to that in a little bit. Back to the neuroprosthetic device. So here's what we do. We either record from the epilepsy patients with electrodes, or we actually record intraoperatively. So this is a patient who's about to get surgery for a tumor removal. You can see the brain pulsing, the heart coming in, electrodes going on. Sound is still not working, guys. Thank you. And what you can see here is this. We put these electrodes on then, and we do some intraoperative experiments. We got about 15 minutes. We put an electrode over the key areas, the language areas, the receptive decoding language areas. And what you find is an unbelievable thing. Here's 9 electrodes, and they're all next to each other. But 8 of these electrodes respond when you hear the word. The one in the middle shuts off, and it responds when you say the word. So this doesn't fit, again, with your cortical organization. There's an incredibly rich microstructure. There's not a blob of this and a blob of that. And probably the microstructure actually goes down to the millimeter level at least with surface recording. So it's a very, very rich signal space. Again, work by Dean Flinker at NYU. And if you take a grid, one of these grids here, and you look, and I present the person with a phoneme like ba for 700 milliseconds, or a word tree. By the way, the black spots are where there's bad contact. You can see you get nice phoneme response all over the place. But for the same amount of acoustic time on, 700 milliseconds, words are really rich. They generate a lot of neural activity. So that provides you with a tremendous amount of data to try to decode what's going on in these brain areas. And you can see we've now gone to 3-millimeter grids, and you can see this is a phoneme representation, a really remarkable amount of activity to actually decode and try to get at this prosthetic device. So a couple things on the way. Categorical perception, we'll see if this works. This has been around since 1956. Categorical perception is a fundamental property of the human brain. We like to bucket things. Instead of taking in everything and analyzing it, we bucket it. We put this there and this there, the dog here, the cat here. And let's see if this plays, guys. Let's try. See if you get categorical perception. It's a ba, da, ga. And you're not going to hear. These are all perfectly spaced, 14 continuous sounds, but you're not going to hear that. You're going to chunk it. And if you don't, it's either the acoustic system or you need to see me after for a neurological evaluation. Take your pick. Okay, guys. Now there's... Try the what? Where? I don't know. That's it. What?
Try that icon to see if there's a slider to actually get volume on. Look, extreme right.
Where? I can't.
I think she's saying right here to the.
Yeah, go to the. Oh, it is up.
It is on. Yeah.
So you got to. This is. What?
You just put your mic down
That's what I'm going to do.
and unplug the audio.
Yeah. Yes?
Yeah, go ahead.
Good. I got to, or else we're toast. Huh?
It's an HDMI though.
Yeah, I don't know what to tell you. Yeah, that's right. Okay. All right. Let's see if you can hear this. Now we have, this is ridiculous. Really ridiculous. Lisa, I got a big problem here. This talk, you got an AV problem. That's pretty, it's probably not allowing this. All right, I don't know what to tell you guys. Anyway, what happens, you'll hear, if you could hear this, you'd hear, you don't hear 14 sounds, you hear ba, and then you transition to da, and then you transition into ga. And we showed initially, so the question was, did you take everything in or did you rapidly chunk it?
I'm going to work on this while you talk.
Okay,
Or would you like to go to another talk and then come back to after?
no. I'm already up here. I'll muddle through. I'll make this unfortunate, but that's life.
All right. This should work out fine now.
What was it? Okay, all right. So we're gonna try? All right, sorry guys. Right, did you hear that? I mean, you were clapping, but it chunks it. And we were able to show physiologically, and this is work done with Eddie Chang, who's doing unbelievable stuff at UCSF. He was in the lab then, that actually by 120 milliseconds, your brain automatically throws things into buckets. So that was nice. So the next thing is, how plastic is your brain? How rapidly does it change? And this is some work being done by Chris Holgraff. And what you're going to hear is these are stimuli that have been degraded, which their spectral temporal receptor fields have been altered to take out any linguistic information. So you're going to hear, you're not going to be able to hear what it says. Then you're going to hear the real phrase. Then you're going to hear the exact same scrambled phrase again. But now, in a second or two, you're going to actually hear and extract language information.
The high-security prison was surrounded by barbed wire. The high-security prison was surrounded by barbed wire.
Same scrambled sound.
The full moon shone brightly that night. Move the garbage near to the large window.
Kind of amazing, right? What's going on? That means your brain is incredibly plastic, right? In 1 second, you change the tuning properties. So now you're changing electrodes to extract language that didn't extract language information before. And since we got a little slowed down, I'll skip some of the technical of how we did it. The bottom line is Chris showed that electrodes that previously were non-linguistic, and when they turn green, they become linguistic from one exposure. And you can see the key areas, of course, the green ones are in auditory cortices. I really applaud Chris because he picked colors that are sensitive to people with color vision. And he actually picked, the colors look a little odd, but they're actually picked specifically because of people who have problems perceiving color. So what about actual speech reconstruction? What's the next step? This is work done by Brian Paisley, and this is the work that more recently is being supported by DARPA in addition to the NIH. You present to the patient with these high-density grids 100 words, and you record the brain electrical activity. You come up with a reconstruction model that forces this activity to match the baseball. Now, as you all know, with enough parameters in a model, you can turn a tsetse fly into an elephant. So you need to confirm your model. So you keep out information, and now you present it to the reconstruction model, and you say, did you just hear a guitar or orangutan? Chances 50-50. Brian got 92% correct. He was able to, this is 2012. So the idea is really simple. We're reading the notes of the cortex. Think of Beethoven, he's deaf. He looks at someone hitting the piano keys, he can reconstruct what that music is. He knows when the key was hit and what frequency was hit. That's what we're doing. We're ascribing to each one of these electrodes a specific frequency at a specific time. That's the spectral temporal component. We're now doing phonemes and syllables and working our way up the food chain, collecting tons of data with continuous recording in the ICU so we can then start applying some deep neural network patterns. So here's what it sounds like. Here's the word the person heard. This is the reconstruction of the word directly from brain recordings.
Walton, oil, structure, doubt, concrete.
That's reconstructed directly from your brain, just from electrical signals. Single phrases reconstructed from the brain. None of that helps the patient. It's pretty cool. We decoded stuff and we can play it back and it sounds cool, but for the patient to have any benefit, you have to be able to decode it when the patient imagines the word, or else it's just a fool's errand, right, in terms of translational. So, God knows. To know when people imagine, that's hard. We basically did the classic, Gettysburg Address, the banner, and then in another condition, the patient either repeated the Gettysburg Address or the banner went by and they imagined it.
4 and 7 years ago, our fathers.
And you can see the comparison of the brain activity from different electrodes, talking and imagining. We then extended that to another study. We've done multiple ones, where in this particular case, there's an auditory cue. You hear the word, let's say, baseball. The visual cue, you imagine baseball. And then another visual cue, and you say baseball. That gives us two decoding models that we can use to try to decode the imagined language. The answer is, can we do it? Yes. It's still in its infancy. We have a lot to do, but we're pretty excited. This is work done by Stephanie Martin, who is a bioengineering student who worked between Berkeley and EPFL. And I'm not going to go into the details. I've already shown you we can decode what you hear. This is us not as robust, but we're decoding what you imagined, the imagined word. That's the key. We can easily do categorical, like, do you want a category, hungry or thirsty? But that's not really decoding the actual word hungry or thirsty. That's our ultimate goal. And we can do the categorization with EEG alone, not with having intracranial. The areas for the decoding, not so surprising to anybody who's involved with language, basically is, again, this posterior temporal area of the brain, Wernicke's area, where if I knock it out, you don't understand language. Broca's area, I can't speak. Wernicke's area, I can't understand. So it fits quite nicely. What about music? Can we decode music? The answer is yes. So this is the iconic Pink Floyd, Another Brick in the Wall. Is there any Pink Floyd fans here? What's wrong with the slide? Tell me. Come on, there's something wrong with this slide. It's not the right album. That's the Dark Side of the Moon, but I used it because it's got the spectral decomposition. It's a little cheesy, but most people don't get it. But it's you gotta amuse yourself when you're doing this stuff. So we had a lot. You do, right? It's hard to do. You gotta be happy. So there's a lot. We had a lot of patients, 28 patients, lots of electrodes, and the informative areas to decode are again in these, early temporal lobe linguistic areas. To cut to the chase, we use the first half of the song to make a model, the second half of the song to decode the second half of the model of the first part of the song, decode the second part. This is the actual song. This is not the decoding. So you could hear words, whistles, music, etc. And this is the actual decoding from the brain. You can hear the voice. Whistle, etc. Why decode music? Why not, I guess. But the other thing, it has prosthetic elements. So if you really want an interface device, you'd like a device that wasn't like, I'm thirsty, I love you. It'd be nice if it had a little emotional prosody in it. So we then did music imagination. This is a young man who contacted us. He's a really accomplished musician. He was 15 at the time. He's actually the co-author on the paper. He basically said, I'm coming to UCSF to get surgery. Can I do some music research? He basically practiced 2 classical pieces for 6 weeks with his keyboard. He either played and listened, or he played and imagined. So again, we had a way to look for the imagine, because we had a mark where his finger hit the keyboard. And cut to the chase, we were able to effectively decode imagine music. This is the distribution of this high-frequency activity that I told you in the perceived and the imagine case. And you can see really very nice. So we're excited. We can easily decode music and speech, and now we're beginning to make inroads into decoding imagine speech with the ultimate goal of an implantable subdural wireless communication device for patients with communication disorders. You can move this back to the cortex in EEG and do all kinds of other things that people want to do. Right now, we're trying to stay tightly focused on making a device for patients. So let me conclude real quickly, because we saw some beautiful stuff with the 3-channel system, but you need, in some places in Africa, I'd like to get them the full system, right? EEG systems are a fortune. Basically, $50,000, $60,000, $70,000. We've got this one down to basically $400. This is a wireless 34-channel EEG with dry electrodes. You put it on, you pop an electrode into one of these holes, and you're recording. That's it, right? And it goes 200 feet. You can go to any device. Our approach is to get it into third world countries and doctors' offices. So what we're doing is we have a project in Uganda where we are training people to use this in the field. So if your kid falls down and you don't know, they jerked, it's a seizure. But if they don't, you don't know. So we do both a heart band, we have a little, obvious little heart band, and we get the head, and then we basically put it to any device. A nurse could do it, a teacher could do it. It goes to the cloud, it goes to Germany. My colleagues in Germany read it, it goes back to Uganda, and they get a report. That's another way to think about providing potable EEG. EEG and water, we're getting both, right? And just so you know, this device is incredibly accurate. This is work done by Julia Kim, who's right there. And if you want to talk to her about this device, she'll be available. You can see this is a target detection task with the classic P3. And you can see we have basically the wet and dry. And if you just look at the target, non-target, target, non-target, they look exactly the same. And we have a separate study in Germany done with the same results. Both of these are being submitted. That one's already in for review. We have a field study being done in neurologist offices in Germany. Same thing for spectral activity. You get beautiful spectral activity. You can imagine the algorithms that Nathan Intrater is using, applying this to this data set. You can extract all kinds of things. So this is your eyes closed. You get a lot of alpha. Eyes closed, wet and dry, beautiful. Again, and this is all work that Julia did in the lab. So 2 more minutes, and am I okay? All right. Turn off the volume? There's no more volume. But this is cool. This is going to be good. But I see the value of the 3-channel device in certain settings. It really depends. You got to be a little bit careful about EEG because your kid could be spiking in the temporal lobe, and you may not exactly pick it up with 3 channels. But those are all technical things that can be figured out from joint collaboration, checking the 2 devices. What I want to talk to you about, here's the people who are responsible for this that you saw today. Actually, Chris is working in Brian Johnson's company. He was a great postdoc, a dean, Flinker at NYU. Ludovic's a French postdoc. Julia's in the audience. And Stephanie is in Geneva looking for what to do next in her career. And Chris has gone into big data. So he'll be mining all your big data and stealing all your thoughts. And be careful, because he's a smart guy and he could probably figure it out. So I just want to introduce one concept to you, not related to making an assistive device or having a wireless EEG or saving the world. This is focused on kids. Now, let me just ask, does anybody in this room not like kids? We're okay? No, because if you didn't like them, you can leave. And that's fine. So here's this new journal, Frontiers for Young Minds. Frontiers for Young Minds is an interesting journal. It's out of the Frontiers series, but it's really different. I'm the chief editor. The gig is this. We bring kids into the scientific review process. They get papers submitted by anybody in here. You published a paper or you want to do a concept review, you submit it. It goes to a kid between the ages of 8 and 14. They are assigned a mentor. Could be anybody in this room could be a mentor for this kid. We're using parents. We're using PhD students, we're using postdocs. The mentor meets with the kid, either real or virtually on Google Hangout. They go over the paper. They provide reviews. They have to know what a hypothesis is, what an experimental design is, what data collection is, what data interpretation is, and how to get it published. Or they can't really review the paper. So we're giving kids at a young age some idea about what the scientific process really is. As I said, it could be a new discovery that you've published. It could be a core concept, for instance, on color vision. Every article, as I mentioned to you, there's a science mentor. It could be a grad student and a couple kids, one kid, a couple kids, a classroom of kids. Every article gets a cartoon. And well, you got to have cartoons if you got a kid's journal, right? I mean, it'd be stupid not to. So basically, I think you could we have 6 divisions, and you probably could figure out that this one is space and astronomy, because that's an article on is there life in other planets. You could probably, this one is our Earth and environment, carbon dioxide extraction. This one, pretty straightforward. Health, what are stem cells? How do they work? How about this one? Jim, you're in the back here. What's a traumatic brain injury, right? So these are the kind of spectrum of the articles. So anybody out here who really wants to be involved in this, get your kid involved. They can sign up as a reviewer. You can sign up as a mentor, or you could submit a paper. But be careful. Be very careful, because these kids are not, they're much harder than all your other reviewers. You know why? They don't care and they're honest. And they just say whatever they want to do. I'll just give you a few reviews and I'll stop. It would be helpful if they told us how they took the measurement of brains without actually having to remove the brain. It's a 9-year-old. How about this one? The writers of the articles did not make it clear why such an expensive and involved research project was done to begin with. It seemed like a fruitless task. Ouch. Ouch. Or, the point is not clearly expressed. I didn't understand the main scientific question because there were so many details at the beginning. Maybe state the main question earlier in the manuscript. These are kids, okay? And then, you think this is good? The next one's my favorite. This is the review, God forbid, you ever get on any of your articles, because this one hurts. This seems important, but the way it is written is so boring, I can't even get to the end. Could the authors maybe sound excited about what they are doing? Right? So anyway, thank you for your attention.